Before anything had shape, before time could be measured or distance could be imagined, there was a state that challenges every instinct of human understanding. It is often described as nothing, yet even that word is misleading, because what existed was not empty space as we think of it today. There were no stars scattered across darkness, no silent void stretching endlessly. There was no space at all, and without space there could be no movement, no direction, no up or down, no before or after. Time itself had no meaning. It did not flow, it did not pause, it simply did not exist. Trying to imagine this state forces the mind into a paradox, because every thought we have relies on space and time. Still, this is where the story of everything begins. The universe, as vast and complex as it is today, emerged from this unimaginable condition. Every galaxy, every atom, every beam of light that has ever traveled across the cosmos was once compressed into a state so dense and so hot that the laws of physics, as we know them, break down. This beginning is not just a distant event in time. It is the origin of all structure, all energy, and all possibility. When we look at the night sky, we are not just observing distant objects. We are looking at a story that began billions of years ago and continues to unfold with every passing moment. In those earliest instants, the universe was incredibly small, far smaller than anything we can visualize. Yet within that tiny state was the potential for everything that would ever exist. Energy dominated completely. There were no atoms, no particles as we recognize them, only an intense, chaotic energy field. As the universe began to expand, this energy started to transform. It cooled, and as it cooled, it began to take on new forms. The very first particles began to emerge, not as stable objects, but as fleeting excitations of energy that appeared and disappeared in fractions of a second. This expansion was not like an explosion in space. It was the expansion of space itself. Every point moved away from every other point, not because they were traveling through a pre-existing void, but because the fabric of reality was stretching. This is one of the most difficult ideas to grasp, yet it is central to understanding the universe. There was no center from which everything expanded. Every location was part of the expansion equally. Even today, this expansion continues, carrying galaxies farther apart as time progresses. As the universe expanded and cooled further, conditions became stable enough for the first fundamental particles to persist. Quarks and electrons began to form, the building blocks of matter. Quarks combined to create protons and neutrons, and these in turn would eventually become the cores of atoms. But at this early stage, the universe was still too hot and energetic for atoms to exist. Particles collided constantly, breaking apart as quickly as they formed. It was a seething, glowing plasma of energy and matter, dense and opaque, where light itself could not travel freely. Time, which had no meaning at the beginning, was now unfolding. With each passing moment, the universe changed. Fractions of a second turned into seconds, seconds into minutes. During these first minutes, a crucial transformation occurred. Protons and neutrons began to combine into simple atomic nuclei. Hydrogen nuclei formed first, followed by helium and small traces of other light elements. This process, known as nucleosynthesis, laid the foundation for all chemical complexity that would come later. Every heavier element that exists today would eventually be built from these simple beginnings. Despite this progress, the universe was still far from the structured cosmos we know. It remained a hot, dense plasma where electrons moved freely, unable to attach to nuclei. Light was trapped, scattered endlessly by charged particles. The universe was glowing, but it was not transparent. It would take hundreds of thousands of years before conditions changed enough for atoms to form completely. When that moment finally arrived, electrons combined with nuclei to create neutral atoms. This event allowed light to travel freely for the first time, filling the universe with a faint glow that still exists today as a relic of that early era. That ancient light continues to travel through space, stretched and cooled by the expansion of the universe. It is one of the most powerful pieces of evidence we have about our origins. It tells us that the universe was once hot and dense, and that it has been expanding ever since. It is a whisper from the past, a signal that has journeyed across billions of years to reach us. When scientists study this light, they are not just observing radiation, they are uncovering a snapshot of the universe when it was still in its infancy. As the universe continued to expand, small variations in density began to play a crucial role. These tiny fluctuations, almost imperceptible differences in the distribution of matter, would eventually grow into the large-scale structures we see today. Gravity, the force that pulls matter together, began to amplify these differences. Regions with slightly more matter attracted even more matter, growing denser over time. Meanwhile, less dense regions became emptier. This process set the stage for the formation of stars, galaxies, and clusters. For millions of years, the universe entered a period often referred to as the cosmic dark ages. There were no stars yet, no galaxies shining across the void. The universe was filled with neutral hydrogen gas slowly clumping under the influence of gravity. It was a quiet, transitional phase where the groundwork for future structure was being laid. Eventually, these clumps grew dense enough to collapse under their own gravity, igniting the first stars. The birth of the first stars marked a turning point in cosmic history. These stars were unlike most of the stars we see today. They were massive, hot, and short-lived. Within their cores, nuclear fusion began to create heavier elements, transforming simple hydrogen and helium into more complex forms. When these stars reached the end of their lives, many of them exploded in powerful supernovae, scattering newly formed elements into space. These elements would later become the building blocks of planets and eventually life itself. The formation of stars led to the formation of galaxies, vast collections of stars bound together by gravity. Over time, galaxies grew and evolved, merging with one another and forming even larger structures. The universe began to take on a web-like appearance, with filaments of galaxies stretching across immense distances and vast empty voids in between. This large-scale structure is still visible today, a testament to the processes that began in the earliest moments of existence. As we look back on this story, it becomes clear that the universe is not static. It is dynamic, constantly changing and evolving. From its earliest moments to the present day, it has undergone countless transformations. What began as a hot, dense state has expanded into a vast cosmos filled with complexity and beauty. Yet, despite all that we have learned, many questions remain. What caused the universe to begin? What lies beyond the observable horizon? Are there other universes, each with their own laws and structures? These questions remind us that our understanding is still incomplete. The universe is not just a collection of objects and forces. It is a mystery that invites exploration. Every discovery leads to new questions, pushing the boundaries of what we know. The journey to understand the universe is ongoing, and it is one of the most profound endeavors humanity has ever undertaken. Standing on a small planet orbiting an ordinary star, we have managed to piece together a story that spans billions of years and unimaginable distances. This achievement is a testament to human curiosity and ingenuity. Through observation, experimentation, and imagination, we have begun to uncover the origins of everything. Yet, the deeper we look, the more we realize how much there is left to discover. The beginning of the universe is not just a scientific concept. It is a story that connects us to everything around us. The atoms in our bodies were forged in the hearts of stars, which themselves formed from the remnants of earlier generations of stars. This chain of creation stretches back to the very beginning, linking us to the origins of the cosmos. In a very real sense, we are part of the universe becoming aware of itself. As this journey continues, we move forward not just with knowledge, but with wonder. The universe invites us to explore, to question, and to imagine. It challenges us to think beyond our everyday experiences and to consider realities that are far removed from our own. In doing so, it expands not only our understanding of the cosmos, but also our perspective on our place within it. And so the story begins, not with a clear image or a simple explanation, but with a profound mystery. From a state beyond comprehension, the universe emerged, evolving over billions of years into the vast and intricate cosmos we see today. This is the foundation upon which all other chapters are built, the starting point of a journey that stretches across time and space, inviting us to explore the unimaginable and to discover what lies beyond. The moment that changed everything did not happen in a place, because there was no place yet for it to occur. It did not happen at a time in the way we understand time, because time itself was only just beginning to take form. Yet this event, known as the Big Bang, marks the starting point of the universe as we know it. It was not an explosion in space, but the rapid expansion of space itself from an unimaginably hot and dense state. In this moment, the fundamental ingredients of reality began to emerge, setting the stage for everything that would follow. At the very earliest fraction of a second, the universe was governed by conditions so extreme that our current understanding of physics struggles to describe them. The four fundamental forces that shape the universe today may have been unified into a single force. Gravity, electromagnetism, and the nuclear forces were not yet distinct. This period is often described through the lens of quantum mechanics, where uncertainty dominates and particles behave more like probabilities than solid objects. In this realm, the universe was not smooth or predictable. It was fluctuating, chaotic, and filled with energy. Almost immediately after the beginning, the universe underwent a dramatic phase known as cosmic inflation. During this brief but crucial period, space expanded at an extraordinary rate, far faster than the speed of light. This does not violate the laws of physics, because it was space itself that expanded, carrying everything with it. Inflation smoothed out the universe on large scales, explaining why it appears so uniform in every direction. At the same time, tiny quantum fluctuations were stretched across vast distances, planting the seeds for all future structure. As inflation ended, the universe continued to expand, but at a slower and more steady rate. The immense energy present during inflation began to convert into particles. This process filled the universe with a hot, dense soup of fundamental particles, including quarks, electrons, and neutrinos. These particles collided constantly, exchanging energy and transforming into different forms. The universe was so hot that particles could not bind together. Any attempt to form stable structures was immediately undone by the intense energy surrounding them. During these first moments, the balance between matter and antimatter played a critical role. For every particle of matter, there was a corresponding particle of antimatter. When these particles met, they annihilated each other, converting their mass into pure energy. If matter and antimatter had existed in perfect balance, they would have completely destroyed each other, leaving behind a universe filled only with radiation. Yet, something unusual happened. There was a slight imbalance, a tiny excess of matter over antimatter. This asymmetry allowed some matter to survive, and that surviving matter would eventually form everything we see today. As the universe expanded further, it began to cool. Cooling allowed quarks to combine into protons and neutrons, the building blocks of atomic nuclei. This marked a significant transition from a chaotic particle soup to a more structured state. Within seconds, the universe had changed dramatically. It was still incredibly hot by everyday standards, but it had cooled enough for new processes to take place. The stage was now set for the formation of the first atomic nuclei. Within the first few minutes, a process known as Big Bang nucleosynthesis occurred. During this time, protons and neutrons combined to form the nuclei of the lightest elements. Hydrogen nuclei formed first, consisting of single protons. Some of these protons combined with neutrons to form helium nuclei. Small amounts of lithium and beryllium were also produced. These elements would remain the dominant forms of matter in the universe for millions of years. Despite the formation of these nuclei, the universe was still far from transparent. It remained a dense plasma of charged particles and radiation. Electrons moved freely, unable to attach themselves to nuclei due to the high-energy environment. Light, in the form of photons, was constantly scattered by these charged particles, preventing it from traveling long distances. The universe was glowing intensely, but it was opaque, like a dense fog of energy and matter. As time passed and expansion continued, the temperature dropped further. After about 380,000 years, conditions became cool enough for electrons to combine with nuclei to form neutral atoms. This event is known as recombination. It marked the moment when light could finally travel freely through space without being constantly scattered. The universe transitioned from opaque to transparent, allowing radiation to move across vast distances. The light released during this time still exists today as the cosmic microwave background, a faint glow that fills the entire universe. This ancient radiation provides a snapshot of the universe at that early stage. It reveals a remarkably uniform temperature, with tiny variations that correspond to slight differences in density. These variations, though incredibly small, were crucial. They represented regions where matter was slightly more concentrated. Over time, gravity would amplify these differences, leading to the formation of stars, galaxies, and the large-scale structure of the universe. One of the key discoveries that supports the idea of an expanding universe came from the observations of Edwin Hubble. He found that distant galaxies are moving away from us, and that the farther away they are, the faster they appear to be receding. This observation is described by Hubble's law. It provided strong evidence that the universe is not static, but expanding, consistent with the predictions of the Big Bang model. The idea of an expanding universe was further supported by the work of Albert Einstein, whose theory of general relativity described how space and time are interconnected and how they respond to matter and energy. Although Einstein initially introduced a term to keep the universe static, he later recognized that his equations naturally predicted expansion. This realization helped lay the foundation for modern cosmology. As scientists continued to study the universe, they developed increasingly detailed models of its early evolution. These models combine observations with theoretical physics to reconstruct what happened in the first moments after the Big Bang. While many details remain uncertain, the overall picture is remarkably consistent. The universe began in a hot, dense state, expanded rapidly, cooled over time, and gradually formed the structures we observe today. Yet the Big Bang is not the end of the story. It is the beginning of a long and complex journey. The processes that followed shaped the universe in profound ways. The formation of atoms, the emergence of structure, and the birth of stars all trace their origins back to those first moments. Every galaxy, every planet, every living being is part of a chain of events that began with the expansion of the universe. There are still mysteries surrounding this origin. What caused the Big Bang? What existed before it, if anything? Some theories suggest that the universe may be part of a larger multiverse, with multiple universes existing simultaneously. Others propose that time itself began with the Big Bang, making the question of what came before meaningless. These ideas push the boundaries of science and philosophy, challenging us to rethink our understanding of reality. Despite these uncertainties, the evidence for the Big Bang is overwhelming. The expansion of the universe, the abundance of light elements, and the presence of the cosmic microwave background all point to a common origin. These observations form a coherent narrative that explains how the universe evolved from its earliest moments to its current state. As we continue to explore the cosmos, new discoveries may refine or even reshape our understanding of the Big Bang. Advances in technology allow us to observe the universe in greater detail, probing deeper into its past. Experiments in particle physics recreate conditions similar to those of the early universe, providing insights into the fundamental forces and particles that governed its evolution. The story of the Big Bang is not just a scientific explanation. It is a profound narrative about the origin of everything. It connects the smallest particles to the largest structures, linking the laws of physics to the existence of galaxies and life itself. It reveals a universe that is dynamic, evolving, and filled with complexity. From an incomprehensibly hot and dense beginning, the universe expanded and cooled, giving rise to matter, energy, and structure. The processes that unfolded in those first moments set the stage for everything that followed. They determined the composition of the universe, the distribution of matter, and the formation of cosmic structures. As we look back on this moment, we are not just studying an event in the distant past, we are uncovering the origin of our own existence. The atoms that make up our bodies were once part of that early universe, shaped by the same processes that formed the stars and galaxies. In this sense, the Big Bang is not just a beginning. It is a connection that links us to the cosmos in a fundamental way. And so the journey continues, moving forward from the birth of the universe into an era of transformation and growth. The next chapters will explore how the first light emerged, how structure began to form, and how the universe evolved into the vast and intricate cosmos we see today. After the violent and incomprehensible beginnings of the Big Bang, the universe entered a new phase, one that would quietly shape everything that followed. The earliest moments had been dominated by extreme energy, rapid expansion, and the formation of the most basic building blocks of matter. But now, as the universe continued to expand and cool, it approached a turning point that would allow light itself to finally travel freely. This moment would mark the true beginning of visibility in the cosmos, the first time the universe could be seen rather than merely inferred. In the hundreds of thousands of years following the initial expansion, the universe remained a dense, hot plasma. Protons and electrons existed, but they were not yet bound together into stable atoms. Photons, or particles of light, were constantly scattered by these free electrons, preventing them from moving in straight lines. The universe during this era was opaque, not because there was a lack of light, but because light was trapped in an endless cycle of collisions. It was a glowing fog, dense with energy and charged particles, where no clear image could form. As time passed, expansion continued to stretch space, causing temperatures to fall steadily. This cooling was not sudden, but gradual, unfolding over hundreds of thousands of years. Eventually, the universe reached a temperature of about 3,000 degrees Kelvin, still incredibly hot by everyday standards, but cool enough for a fundamental change to occur. Electrons began to slow down enough to be captured by protons, forming neutral hydrogen atoms. Helium nuclei also captured electrons, forming neutral helium atoms. This process is known as recombination, although it was technically the first time these particles combined. With the formation of neutral atoms, the behavior of light changed dramatically. Photons were no longer constantly scattered by free electrons. Instead, they were able to travel vast distances without interruption. For the first time in cosmic history, the universe became transparent. Light could move freely, carrying information about the state of the universe at that moment. This ancient light still exists today as the cosmic microwave background, often abbreviated as CMB. The CMB is one of the most important discoveries in cosmology. It represents a snapshot of the universe approximately 380,000 years after the Big Bang. At that time, the universe was remarkably uniform, with nearly the same temperature in every direction. However, careful measurements reveal tiny fluctuations, differences in temperature that are only a few millionths of a degree. These fluctuations correspond to slight variations in density, regions where matter was just a bit more or less concentrated than average. These tiny differences would eventually grow into the vast structures we see today. Under the influence of gravity, denser regions began to pull in more matter, becoming even denser over time. Less dense regions lost matter and became emptier. This process, known as gravitational instability, is the mechanism by which structure forms in the universe. It is a slow and gradual process, unfolding over millions and billions of years, but its origins can be traced back to those tiny fluctuations in the early universe. Despite the newfound transparency of the universe, it did not immediately become filled with stars and galaxies. Instead, it entered a long period, often referred to as the cosmic dark ages. During this time, the universe was filled mostly with neutral hydrogen gas. There were no stars to emit visible light, and so the universe, while transparent, was largely dark. The CMB provided a faint background glow, but it had already begun to stretch into longer wavelengths due to the ongoing expansion of space. This expansion continued to cool the universe further, and as it did, the matter within it began to clump together more effectively. Regions that were slightly denser than average attracted more matter, forming increasingly large clouds of gas. These clouds were not uniform. They had complex internal motions, with turbulence and rotation playing important roles. Over time, some regions within these clouds became dense enough to collapse under their own gravity. As these collapsing regions grew denser, they began to heat up. The conversion of gravitational energy into thermal energy caused temperatures to rise in the cores of these clouds. Eventually, conditions became extreme enough for nuclear fusion to ignite. Hydrogen atoms began to fuse into helium, releasing enormous amounts of energy. This marked the birth of the first stars, bringing an end to the cosmic dark ages. These first stars were very different from the stars we see today. Known as population 3 stars, they were composed almost entirely of hydrogen and helium, the only elements that existed in significant quantities at the time. Without heavier elements to cool the gas, these stars grew extremely large, often hundreds of times more massive than the Sun. Their immense mass made them incredibly bright and hot, but also very short-lived. Many of them burned through their fuel in just a few million years. The light from these first stars began to transform the universe once again. Their intense radiation ionized the surrounding hydrogen gas, stripping electrons from atoms and returning the universe to a partially ionized state. This period is known as re-ionization. It marked a second major transition in the universe's history, as light from stars and galaxies reshaped the cosmic environment. As more stars formed, they began to group together under the influence of gravity, forming the first galaxies. These early galaxies were small and irregular, far from the majestic spirals and ellipticals we see today. Over time, they merged and grew, building larger and more complex structures. The universe began to take on a web-like pattern, with galaxies forming along vast filaments of matter separated by enormous voids. The role of dark matter in this process was crucial. Although it cannot be seen directly, dark matter exerts gravitational influence, helping to pull ordinary matter into dense regions. It acts as a scaffold upon which galaxies form. Without it, the structures we observe today would not have had enough time to develop within the age of the universe. While the formation of stars and galaxies marked a significant step forward, the light from the earliest times continued its journey across the cosmos. The CMB, once composed of visible and infrared light, has been stretched by the expansion of the universe into microwave wavelengths. It now fills all of space, providing a faint but measurable signal that carries information about the early universe. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson provided strong evidence for the Big Bang theory. They detected a uniform background noise in their radio antenna, which turned out to be the remnant radiation from the early universe. This discovery confirmed that the universe had once been in a hot, dense state and had cooled over time. Subsequent missions, such as those involving space telescopes, have mapped the CMB in incredible detail. These maps reveal the tiny fluctuations in temperature that correspond to the seeds of cosmic structure. By studying these patterns, scientists can learn about the composition, age, and evolution of the universe. The CMB is not just a relic of the past. It is a tool that allows us to probe the fundamental properties of the cosmos. As we consider this era, it becomes clear that the emergence of light was not a single event, but a series of transitions. First came the release of the CMB, the moment when the universe became transparent. Then came the formation of the first stars, bringing visible light back into the cosmos. Together, these events transformed the universe from a dark, featureless expanse into a dynamic and luminous environment. The journey from darkness to light is one of the most profound transformations in cosmic history. It represents the transition from simplicity to complexity, from uniformity to structure. It is the foundation upon which all later developments are built. Without the processes that occurred during this time, there would be no stars, no galaxies, no planets, and no life. Even today, the light from those early times continues to travel through space, carrying with it the story of the universe's infancy. When we observe the cosmos with powerful telescopes, we are looking back in time, seeing objects as they were billions of years ago. The farther we look, the closer we come to the beginning. In this way, the universe allows us to explore its own history, revealing its secrets layer by layer. The emergence of light also has a deeper significance. It represents the moment when the universe became observable, when it transitioned from a hidden state to one that could, in principle, be seen and understood. It is the beginning of a narrative that we, as observers, are now part of. By studying this light, we are not just learning about the universe, we are connecting with its earliest moments. As the universe continued to evolve, the structures that formed during this period would grow and interact in increasingly complex ways. Galaxies would collide and merge, stars would be born and die, and new elements would be created in the hearts of stars. The simple beginnings of hydrogen and helium would give rise to the rich chemical diversity we see today. This chapter of the universe's story is one of quiet transformation, where small changes lead to profound consequences. The formation of atoms, the release of light, and the growth of structure all set the stage for everything that follows. It is a reminder that even the smallest fluctuations can have enormous effects over time. From a nearly uniform sea of particles and radiation, the universe began to develop patterns and structures. These patterns would eventually lead to the formation of galaxies, stars, and planets. They would create the conditions necessary for life to emerge, and they would allow the universe to become aware of itself through the minds of beings capable of observation and understanding. As we move forward in this journey, we carry with us the knowledge that the light we see today is a message from the past. It tells a story of transformation, of emergence, and of possibility. It reminds us that the universe is not static, but ever-changing, shaped by the forces that were set in motion at its very beginning. As the faint glow of the cosmic microwave background faded into longer wavelengths and the universe continued its steady expansion, a new era quietly took shape. The universe, once a nearly uniform sea of particles and radiation, began to show the first signs of structure. What had started as tiny fluctuations in density, barely noticeable differences in the distribution of matter, now began to grow under the persistent pull of gravity. These slight imbalances would ultimately give rise to the first stars and galaxies, transforming the cosmos from a dark and featureless expanse into a complex and luminous environment. In this early stage, the universe was dominated by vast clouds of neutral hydrogen and helium gas. There were no stars yet, no galaxies shining in the darkness, only immense regions of matter slowly drifting and clustering. The expansion of space continued to stretch everything apart, but within these clouds, gravity worked in opposition, pulling matter inward. Over time, certain regions became denser than others. These denser regions began to collapse under their own weight, initiating the process that would lead to the birth of the first stars. A critical but invisible component played a major role in this transformation: dark matter. Although it does not emit or absorb light, dark matter exerts gravitational influence. It formed a kind of cosmic framework, a hidden scaffolding upon which ordinary matter could accumulate. Regions rich in dark matter created gravitational wells, drawing in gas and helping it clump together more efficiently. Without this unseen force, the formation of structure in the universe would have been far slower, and the galaxies we see today might never have formed. As gas clouds continued to collapse, their interiors grew denser and hotter. The process was gradual but relentless. Gravity pulled matter inward, increasing pressure and temperature at the core of these collapsing regions. Eventually, conditions became extreme enough to ignite nuclear fusion. Hydrogen atoms began to fuse into helium, releasing enormous amounts of energy. This marked the birth of the first stars, ending the long cosmic dark ages and bringing light back into the universe. These first stars, often referred to as population 3 stars, were unlike the stars we are familiar with today. They formed in an environment that lacked heavier elements, meaning the gas from which they formed could not cool efficiently. As a result, these stars grew incredibly massive, often hundreds of times the mass of the Sun. Their immense size made them extraordinarily bright and hot, emitting intense radiation that would have illuminated the surrounding darkness. However, their brilliance came at a cost. Massive stars burn through their fuel quickly, and these early stars were no exception. Many of them lived for only a few million years, a brief lifespan compared to stars like our Sun, which can exist for billions of years. When these massive stars reached the end of their lives, they often exploded in powerful supernovae. These explosions were among the most energetic events in the universe, releasing vast amounts of energy and scattering newly formed elements into space. Inside the cores of these first stars, nuclear fusion created elements heavier than hydrogen and helium. Elements such as carbon, oxygen, and iron were forged through a series of fusion reactions. When the stars exploded, these elements were ejected into the surrounding space, enriching the interstellar medium. This process marked the beginning of chemical evolution in the universe. The simple composition of the early cosmos began to give way to increasing complexity, laying the groundwork for the formation of planets and, eventually, life. As more stars formed and died, the universe became progressively enriched with heavier elements. New generations of stars formed from this enriched material, leading to a diversity of stellar types and characteristics. These later stars were generally smaller and longer-lived than the first generation, as the presence of heavier elements allowed gas clouds to cool more efficiently and fragment into smaller pieces. At the same time, stars did not form in isolation. They began to group together under the influence of gravity, forming the earliest galaxies. These protogalaxies were small and irregular, far different from the well-defined structures we see today. They contained clusters of stars, gas, and dark matter, all bound together by gravity. Over time, these structures grew through a process of merging and accretion, combining with other protogalaxies to form larger systems. The formation of galaxies was not a simple or orderly process. It involved complex interactions between gravity, gas dynamics, and radiation. Collisions and mergers were common, reshaping galaxies and triggering bursts of star formation. These interactions played a key role in determining the shapes and properties of galaxies. Some evolved into spiral galaxies, with rotating disks and sweeping arms, while others became elliptical galaxies, more rounded and less structured. The large-scale structure of the universe also began to emerge during this period. Galaxies were not distributed randomly, but instead formed a vast cosmic web. This web consists of filaments of galaxies and dark matter stretching across immense distances, intersecting at dense nodes known as galaxy clusters. Between these filaments lie enormous voids, regions with very little matter. This structure reflects the initial fluctuations in density from the early universe, amplified over billions of years by gravity. One of the most remarkable aspects of this process is how it connects the smallest scales to the largest. Tiny quantum fluctuations in the early universe, stretched by cosmic inflation, eventually led to the formation of galaxies and clusters spanning millions of light-years. The same fundamental laws of physics govern both extremes, linking the behavior of subatomic particles to the evolution of the cosmos. As galaxies continued to grow and evolve, they became sites of intense activity. Star formation occurred in dense regions of gas, often triggered by interactions or collisions. Supernova explosions enriched the surrounding medium and influenced future star formation. Black holes, formed from the collapse of massive stars, began to appear and grow. In the centers of many galaxies, supermassive black holes formed, exerting powerful gravitational influence and sometimes producing energetic jets that could extend far beyond the galaxy itself. The light from these early stars and galaxies played another crucial role in shaping the universe. Their radiation ionized the surrounding hydrogen gas, marking the period known as reionization. This process gradually transformed the universe from a neutral state back into an ionized one, allowing light to travel more freely over large distances. By the end of this era, the universe had become largely transparent, similar to how it is today. Observing this period directly is challenging, as it occurred billions of years ago and at great distances. However, modern telescopes allow us to look back in time by observing distant galaxies whose light has taken billions of years to reach us. Instruments such as the James Webb Space Telescope have provided unprecedented views of the early universe, revealing galaxies that formed only a few 100 million years after the Big Bang. These observations offer valuable insights into how the first structures formed and evolved. As we study these distant objects, we begin to piece together a picture of the universe's early development. We see how small fluctuations grew into massive structures, how the first stars ignited and enriched the cosmos, and how galaxies formed and evolved over time. Each observation adds a new piece to the puzzle, helping us understand the processes that shaped the universe. The formation of stars and galaxies represents a major transition in cosmic history. It marks the shift from a simple, nearly uniform universe to one filled with complexity and diversity. It is the beginning of the structures that would eventually lead to planets, solar systems, and life. Without this phase, the universe would remain a dark and featureless expanse, lacking the richness we observe today. This chapter of the universe's story is one of creation and transformation. It shows how the interplay of gravity, energy, and matter can give rise to extraordinary structures. It highlights the importance of small beginnings, where tiny fluctuations can lead to immense consequences over time. And it reveals the dynamic nature of the cosmos, constantly evolving and reshaping itself. As we move forward, the galaxies formed during this era will continue to grow and interact. They will merge, collide, and evolve into the diverse forms we see in the present universe. Within them, new generations of stars will form, some of which will host planetary systems. The elements created in the first stars will become part of planets, oceans, and living organisms. The story of the first stars and galaxies is not just about distant objects in space. It is about the origins of structure and complexity. It is about how the universe transformed from simplicity into something capable of supporting life and consciousness. It is a reminder that everything we see today, from the smallest particle to the largest galaxy, is part of a continuous process that began billions of years ago. In the vastness of space and time, these early events may seem distant and abstract, yet they are deeply connected to our existence. The atoms in our bodies were forged in stars, the descendants of those first luminous giants. The galaxies that fill the night sky are the result of processes that began in this early era. By understanding this chapter, we gain insight into the origins of everything around us. And so, the universe continues its journey, moving from the birth of stars and galaxies toward ever greater complexity. What began as a simple distribution of matter and energy has evolved into a cosmos rich with structure and possibility. The next steps in this journey will bring us closer to home, exploring the formation of our own galaxy and the place we occupy within this vast and ever-changing universe. Amid the vast cosmic web of galaxies that emerged from the early universe, one particular system would come to hold special significance. It is a sprawling, rotating collection of stars, gas, dust, and dark matter known as the Milky Way. From a distance, it would appear as a graceful spiral, its luminous arms winding outward from a dense and energetic center. But from within, it is far more than just a shape in space. It is a dynamic and evolving system, one that has been forming and changing for billions of years, and one that would eventually give rise to a small planetary system capable of observing and understanding it. The Milky Way did not appear suddenly in its present form. Like all galaxies, it formed gradually through a process of accumulation and merging. In the early universe, smaller protogalaxies began to form from collapsing clouds of gas and dark matter. These smaller structures were drawn together by gravity, colliding and combining over time. Each merger brought in new stars, gas, and dark matter, building up the mass of what would eventually become the Milky Way. In its earliest stages, the Milky Way was likely a chaotic and irregular system. Stars formed rapidly, often in bursts triggered by collisions and interactions with other young galaxies. Gas clouds flowed inward, feeding star formation and contributing to the growth of the galaxy's central region. Over time, as the rate of major collisions decreased, the galaxy began to settle into a more stable structure. A rotating disk formed, flattening out as angular momentum shaped its motion. Within this disk, spiral arms began to emerge, regions of higher density where stars continued to form. At the heart of the Milky Way lies a region of intense activity and immense gravitational power. This central area, known as the galactic core, is home to a supermassive black hole called Sagittarius A. With a mass millions of times greater than that of the Sun, it exerts a powerful influence on its surroundings. Stars near the center move at incredible speeds, their orbits shaped by the black hole's gravity. Although it is currently relatively quiet compared to the active cores of some other galaxies, it remains a dominant presence in the structure of the Milky Way. Surrounding the central core is a dense region known as the bulge, composed of older stars packed closely together. Beyond this lies the galactic disk, the most recognizable part of the Milky Way. The disk contains billions of stars, as well as vast clouds of gas and dust. It is within this disk that the spiral arms are found. These arms are not rigid structures, but rather regions where density waves move through the galaxy, compressing gas and triggering the formation of new stars. The spiral arms are sites of ongoing creation. Within them, massive clouds of gas collapse under gravity, forming new stars and planetary systems. These regions are often illuminated by the bright light of young, hot stars, creating some of the most visually striking features in the galaxy. Over time, stars drift out of these arms, moving into more stable orbits within the disk. This continuous cycle of star formation and movement gives the Milky Way its dynamic character. Beyond the disk lies the galactic halo, a vast and sparsely populated region that extends far beyond the visible structure of the galaxy. The halo contains old stars, globular clusters, and a significant amount of dark matter. While it is less dense than the disk, it plays an important role in the overall mass and gravitational behavior of the Milky Way. The presence of dark matter in the halo helps to explain why stars in the outer regions of the galaxy orbit at speeds that cannot be accounted for by visible matter alone. The Milky Way is not an isolated system. It is part of a small group of galaxies known as the Local Group. This group includes several dozen galaxies the most notable of which is the Andromeda galaxy. The Milky Way and Andromeda are the two largest members of this group, and they are slowly moving toward each other under the influence of gravity. In several billion years, they are expected to collide and merge, forming a new, larger galaxy. The Milky Way is a system of immense scale. It contains hundreds of billions of stars and spans over 100,000 light-years in diameter. Yet, it is just one of countless galaxies in the observable universe. Each galaxy has its own history, structure, and characteristics. By studying the Milky Way, we gain a deeper understanding of galaxies in general, as well as our place within the cosmos. The story of the Milky Way is one of gradual growth and continuous change. It has been shaped by gravity, enriched by generations of stars, and influenced by interactions with other galaxies. It is both a product of the early universe and an active participant in its ongoing evolution. As planetesimals collided and merged, they formed protoplanets, the early stages of planets. This process was not smooth or orderly. Collisions were often violent, with impacts releasing enormous amounts of energy. Some collisions led to growth, while others shattered objects into smaller pieces. Over millions of years, a few dominant bodies emerged, clearing their orbits and becoming the planets of the solar system. As time passed, the solar system began to settle. The frequency of large collisions decreased, and the planets established more stable orbits. The sun continued to shine, providing a steady source of energy. On the planets, processes such as volcanic activity, atmospheric development, and surface evolution began to shape their environments. Each planet followed its own path, influenced by its size, composition, and distance from the Sunday. Earth, in particular, underwent a series of transformations that would make it unique. Its position in the habitable zone, where temperatures allow for liquid water, played a critical role. Water delivered by comets and asteroids or released from the planet's interior accumulated on the surface, forming oceans. The presence of a magnetic field helped protect the planet from harmful solar radiation, while geological activity recycled materials and maintained a dynamic surface. The formation of the solar system is not just a story of planets and orbits, it is a story of how complexity arises from simple beginnings. From a cloud of gas and dust, a structured system emerged, governed by the laws of physics and shaped by countless interactions. The same processes that formed our solar system are thought to occur around other stars, suggesting that planetary systems may be common throughout the galaxy. As we look outward from Earth, we see a system that is both familiar and extraordinary. The planets, moons, and other objects that make up the solar system are part of a larger cosmic narrative, one that continues to unfold. Each discovery adds to our understanding, revealing new details about how this system formed and how it fits into the broader universe. From the collapse of a cloud to the formation of a star and its planets, the journey of the solar system is a story of transformation and connection. It is a reminder that even the most ordinary star can give rise to something remarkable. And within this system, on a small rocky planet orbiting at just the right distance from its star, the next chapter of this story begins, one that will explore the emergence of life and the conditions that made it possible. Within the evolving structure of the solar system, one planet formed under conditions that would eventually allow something extraordinary to emerge. Among the rocky worlds orbiting the Sun, the Earth occupies a unique position. Its distance from the Sun places it within a region often referred to as the habitable zone, where temperatures are suitable for liquid water to exist on the surface. Yet, distance alone does not explain what makes Earth special. Its story is one of transformation. shaped by violent beginnings, dynamic processes, and a delicate balance of conditions that would ultimately give rise to life. As oxygen levels increased, more complex forms of life began to evolve. Cells developed internal structures, leading to the emergence of eukaryotic cells, which are larger and more complex than prokaryotic cells. These cells eventually gave rise to multicellular organisms, marking a major step in the evolution of life. Over time, these organisms diversified, adapting to different environments and developing new forms and functions. The surface of Earth also continued to change during this time. The movement of tectonic plates reshaped continents and oceans, creating a constantly evolving landscape. Mountains rose and eroded. Oceans opened and closed, and climates shifted over millions of years. These changes influenced the distribution and evolution of life, creating new opportunities and challenges. Life on Earth has not been a steady progression. It has been shaped by periods of stability as well as episodes of dramatic change. Mass extinctions, caused by events such as volcanic eruptions, climate shifts, and asteroid impacts, have periodically wiped out large numbers of species. Yet each time, life has recovered and diversified, filling ecological niches and evolving new forms. One of the most well-known of these events is the extinction that marked the end of the dinosaurs, caused by a massive asteroid impact. This event reshaped the course of evolution, allowing mammals to rise and eventually dominate the planet. From these mammals would eventually emerge primates, and from primates, humans. In the most massive stars, this collapse is catastrophic. The core implodes under its own weight, compressing matter to an extraordinary degree. Protons and electrons are forced together, forming neutrons, and the outer layers of the star are expelled in a violent supernova explosion. What remains depends on the mass of the original star. If the core is massive enough, not even neutron degeneracy pressure can stop the collapse. The core continues to shrink until it forms a black hole, a point where density becomes effectively infinite and gravity becomes overwhelming. At the boundary of a black hole lies the event horizon. This is not a physical surface, but a region in space that marks the point of no return. Once an object crosses this boundary, it cannot escape the black hole's gravitational pull. From the outside, it appears as if time slows down near the event horizon. Objects falling toward it seem to stretch and fade, never quite crossing the boundary from the perspective of a distant observer. This strange behavior arises from the effects of general relativity, which describes how mass and energy warp the fabric of space-time. A black hole represents an extreme case of this warping, where space-time is curved so dramatically that all paths lead inward. At the center of a black hole lies what is known as a singularity, a point where current theories predict that density becomes infinite and the known laws of physics break down. Black holes come in different sizes. Stellar mass black holes form from the collapse of individual stars and typically have masses several times that of the Sunday. Supermassive black holes, on the other hand, reside at the centers of galaxies and can have masses millions or even billions of times greater than the Sunday. The Sagittarius A times at the center of the Milky Way is one such example, influencing the motion of stars in its vicinity. Extreme objects also play a role in shaping galaxies and the larger universe. Supermassive black holes can influence star formation by heating or expelling gas, regulating the growth of their host galaxies. Their jets can extend across thousands of light years, impacting the surrounding environment. These interactions highlight the interconnected nature of cosmic processes, where even the most extreme phenomena contribute to the evolution of the universe. As we continue to explore these objects, new discoveries are likely to challenge our understanding and reveal new aspects of the cosmos. The study of extreme objects is still in its early stages, with many questions yet to be answered. Advances in technology, such as more sensitive detectors and powerful telescopes, will allow us to observe these phenomena in greater detail and across different wavelengths. From the collapse of massive stars to the merging of black holes, the universe is filled with events that push the limits of what is possible. These extreme objects remind us that the cosmos is not just vast, but also dynamic and often violent. They show that the same laws of physics that govern everyday experiences can lead to extraordinary outcomes under the right conditions. In the context of the broader cosmic story, extreme objects represent both endpoints and transitions. They mark the deaths of stars, the centers of galaxies, and the sources of powerful energy. Yet, they also contribute to new beginnings, creating elements and influencing the formation of future structures. They are both destructive and creative, embodying the dual nature of the universe. Dark energy is even more mysterious than dark matter. It does not clump together or form structures. Instead, it appears to be uniformly distributed throughout space, exerting a repulsive effect that causes the expansion of the universe to accelerate. The nature of dark energy is not well understood, but it is thought to make up the largest portion of the universe's total energy content. One way to think about dark energy is as a property of space itself. As the universe expands, more space is created, and with it, more dark energy. This leads to an accelerating expansion, where galaxies move away from each other at an increasing rate. Over vast timescales, this expansion could have profound consequences for the future of the universe. The discovery of dark energy has reshaped our understanding of cosmology. It suggests that the fate of the universe is not determined solely by gravity and the amount of matter it contains, but also by this mysterious force that pushes space apart. Depending on its properties, dark energy could lead to different scenarios for the ultimate fate of the cosmos, from a gradual cooling and dilution to more extreme possibilities. Cosmic collisions also play a role in the distribution of chemical elements. When galaxies merge, gas clouds mix and new stars are formed. These stars synthesize heavier elements through nuclear fusion, and when they die, they release these elements back into space. Over time, this process enriches the interstellar medium, increasing the abundance of elements necessary for planet formation and, ultimately, life. The history of cosmic collisions is therefore closely linked to the history of matter itself. From the earliest galaxies to the present day, interactions between systems have driven the redistribution of energy and material. They have shaped the evolution of galaxies, influenced the formation of stars, and contributed to the chemical complexity of the universe. Even on smaller scales, similar principles apply. Within galaxies, star clusters can interact, and within planetary systems, objects can collide and merge. These processes reflect the same underlying physics that governs galaxy collisions, scaled down to different environments. Gravity remains the dominant force, shaping motion and structure across all scales. As we observe the universe more deeply, we find evidence of collisions at every level. Distant galaxies show signs of past interactions with distorted shapes and tidal structures. Closer to home, the history of our own galaxy reveals a record of past mergers with smaller systems. The Milky Way has grown over time by absorbing dwarf galaxies, leaving behind streams of stars that trace their paths through space. These stellar streams are remnants of past collisions, stretched out over vast distances by gravitational forces. They serve as archaeological evidence of the galaxy's history, allowing astronomers to reconstruct events that occurred billions of years ago. By studying these structures, scientists can learn about the formation and evolution of the Milky Way in detail. Cosmic collisions are not just destructive events, they are also creative processes that drive the evolution of the universe. Through interactions and mergers, galaxies grow, transform, and evolve. New stars are formed, chemical elements are distributed, and structures become more complex. The universe becomes richer and more diverse as a result of these interactions. At the same time, these events remind us of the dynamic nature of the cosmos. Nothing in the universe remains fixed forever. Even the largest structures are subject to change over time. Galaxies that appear stable today will eventually interact, merge, or evolve into new forms. The universe is in a constant state of motion and transformation. As we continue to study cosmic collisions, we gain a deeper understanding of how the universe evolves. We see that structure is not static, but constantly reshaped by gravity and motion. We learn that even seemingly violent events can lead to creation and growth. And we begin to understand that the universe is a connected system where every interaction contributes to its overall evolution. In the next stage of this journey, the focus will shift from the interactions between galaxies to the broader behavior of the universe itself. We will explore how space is expanding, how this expansion affects everything within it, and how the future of the cosmos is shaped by this ongoing process. Across the vast stretches of the universe, galaxies are not only shaped by collisions, gravity, and internal evolution, but also by something even more fundamental: the expansion of space itself. This expansion is not an outward movement into empty void, but rather a stretching of the fabric of reality. Every region of space is moving away from every other region, carrying galaxies along with it. This discovery transformed our understanding of the cosmos and revealed that the universe is not static, but dynamic on the largest possible scale. The first clues that the universe was expanding came from careful observations of distant galaxies. When astronomers studied the light from these galaxies, they noticed that the light was shifted toward the red end of the spectrum. This phenomenon, known as redshift, occurs when an object is moving away from the observer. The greater the distance of the galaxy, the greater the redshift observed in its light. This relationship suggested that galaxies are not only moving, but that space itself is expanding between them. This observation was formalized through what is now known as Hubble's law. This law describes how the speed at which a galaxy appears to be moving away from us is proportional to its distance. The farther away a galaxy is, the faster it appears to recede. This pattern is not due to galaxies moving through space in a traditional sense, but rather because space itself is stretching uniformly in all directions. The discovery of this expansion was closely associated with the work of Edwin Hubble, who made systematic observations of galaxies beyond the Milky Way. His measurements provided strong evidence that the universe is not static, as once believed, but is instead evolving over time. This realization fundamentally changed cosmology and opened the door to modern theories of the universe's origin and evolution. The concept of an expanding universe is deeply rooted in the framework of general relativity developed by Albert Einstein. This theory describes how mass and energy curve space-time and how this curvature determines the motion of objects. When applied to the universe as a whole, The equations of general relativity naturally allow for dynamic solutions in which space itself can expand or contract. At the largest scales, the expansion of the universe is remarkably uniform. No matter where we look, galaxies appear to be moving away from each other in all directions. This gives the impression that every observer, regardless of location, would see the same general pattern of expansion. There is no central point from which the expansion originates. Instead, every point in space can be considered part of the expansion. To understand this more clearly, imagine the universe not as objects moving through space, but as space itself, stretching like the surface of a balloon being inflated. As the balloon expands, all points on its surface move away from each other. There is no center on the surface itself, yet all distances increase. In a similar way, galaxies are carried apart by the expansion of space. However, this expansion does not affect all structures equally. On small scales, such as within galaxies, solar systems, or even clusters of galaxies, gravitational forces are strong enough to hold systems together. The Milky Way, for example, is not expanding. Its stars remain bound by gravity, and its structure remains intact. Expansion becomes significant only on much larger scales, where gravity is weaker than the effect of expanding space. The rate of expansion is described by a quantity known as the Hubble constant. This value represents how quickly space is expanding per unit distance. By measuring the redshift of distant galaxies and their distances from us, scientists can estimate this rate. Although there is some uncertainty in its exact value, the Hubble constant provides a crucial tool for understanding the age and size of the universe. One of the most profound implications of an expanding universe is that it must have been smaller in the past. If we imagine reversing the expansion, we find that galaxies would come closer together, eventually converging into a much denser and hotter state. This idea forms the basis of the Big Bang model, which describes the universe as having evolved from an extremely compact beginning. As the universe expands, it also cools. This is because the energy of photons, or particles of light, decreases as their wavelengths are stretched by the expansion of space. This process causes the overall temperature of the universe to drop over time. In the early universe, temperatures were so high that matter existed in a plasma state. As expansion continued, the universe cooled enough for atoms, stars, and galaxies to form. The expansion of the universe also affects the way we observe distant objects. Because light takes time to travel across space, we are always seeing distant galaxies as they were in the past. The farther away a galaxy is, the older the light we receive from it. This means that by observing distant regions of the universe, we are effectively looking back in time. In this way, the universe itself acts as a natural time machine. As we look deeper into space, we see galaxies in different stages of their evolution. Nearby galaxies appear more developed, while very distant galaxies appear younger and more irregular. Some of the most distant galaxies observed are seen as they were only a few 100 million years after the Big Bang. These observations provide valuable insights into how galaxies form and evolve over time. One of the most important discoveries in modern cosmology is that the expansion of the universe is not slowing down, but accelerating. This surprising result was first observed in the late 20th century through studies of distant supernovae. These exploding stars serve as standard candles, allowing astronomers to measure distances across the universe. The data revealed that distant galaxies are receding faster than expected, indicating that the expansion rate is increasing. This accelerated expansion is attributed to a mysterious component of the universe known as dark energy. Unlike matter, which pulls objects together through gravity, dark energy appears to push space apart. It is evenly distributed throughout the universe and becomes more significant as space expands. Although its exact nature is unknown, it is thought to make up the majority of the universe's total energy content. The presence of dark energy has profound implications for the future of the universe. If the acceleration continues, galaxies outside of our local group will eventually move away faster than the speed at which their light can reach us. Over vast timescales, this will cause them to disappear from our observable universe, leaving only nearby galaxies visible in the distant future. This leads to a scenario in which the universe becomes increasingly isolated. As expansion continues, galaxies become more widely separated, and the night sky becomes darker over time. Eventually, distant galaxies will fade from view, and the observable universe will shrink to include only gravitationally bound systems. This outcome is sometimes referred to as the cosmic isolation scenario. However, the exact nature of dark energy remains one of the greatest mysteries in physics. Some theories suggest that it may be a property of space itself, similar to a cosmological constant introduced by Albert Einstein in his equations of general relativity. Others propose that it could be related to dynamic fields that change over time. Determining its true nature is one of the central challenges in modern cosmology. The expansion of the universe also raises deep philosophical questions about the nature of space and time. If space is expanding, what is it expanding into? The answer, according to current understanding, is that space is not expanding into anything. Instead, space itself is the fabric of reality, and it is this fabric that is stretching. There is no external container. The universe contains all of space and time within itself. Observational evidence for expansion comes from multiple sources, not just galaxy redshift. The distribution of the cosmic microwave background provides a snapshot of the early universe, showing how small fluctuations grew into large-scale structures. The abundance of light elements also supports the idea that the universe was once much hotter and denser. Together, these lines of evidence form a consistent picture of cosmic evolution. Modern telescopes and surveys continue to refine our understanding of expansion. By mapping millions of galaxies, scientists can trace how structure grows over time and how expansion influences this growth. These observations help test different models of dark energy and improve our estimates of the universe's age and composition. The expansion of the universe is not just a physical process, it is also a framework that connects all of cosmic history. From the earliest moments after the Big Bang to the formation of galaxies and the present day, expansion has shaped every stage of evolution. It provides the backdrop against which all cosmic events unfold. As we reflect on this process, it becomes clear that the universe is not a static stage, but an evolving system. Its size, structure, and behavior change over time. The galaxies we see today will not remain in the same positions forever. They are part of a larger flow, carried by the expansion of space itself. In the next stage of this journey, we will move from the large-scale behavior of the universe to one of its most profound questions, whether we are alone. The focus will shift toward distant worlds beyond our solar system, where the conditions for life may or may not exist, and where the possibility of other forms of life opens new dimensions in our understanding of the cosmos. As the universe expands and galaxies drift farther apart, one of the most profound questions emerges from within a small corner of the cosmos. Is life unique to Earth? or is it a widespread phenomenon scattered across the stars? On our own planet, life arose under conditions that combined chemistry, energy, and time in a delicate balance. But the universe is vast beyond comprehension, filled with billions of galaxies, each containing billions of stars, many of which host planetary systems. Within this immense expanse lies the possibility that life may not be limited to a single world. The search for life beyond Earth begins with understanding how planets form and where suitable conditions might exist. Around stars, similar to the Sun, planets can form within a disk of gas and dust. Some of these planets may lie within a region known as the habitable zone, where temperatures allow liquid water to exist on a surface. Liquid water is considered one of the key ingredients for life as we know it, making these regions prime targets in the search for habitable worlds. The discovery of planets outside our solar system, known as exoplanets, has transformed this field of study. Using advanced telescopes and detection methods, astronomers have identified thousands of these distant worlds orbiting other stars in the Milky Way. Some are rocky, like Earth, while others are gas giants or ice worlds. Many of these planets exist in conditions very different from anything found in our own solar system, expanding our understanding of what kinds of environments can exist in the universe. One of the primary methods used to detect exoplanets is the transit method. When a planet passes in front of its host star, it causes a slight dimming of the star's light. By measuring these tiny changes in brightness, scientists can determine the size and orbital period of the planet. Another method involves measuring the wobble of a star caused by the gravitational pull of an orbiting planet. These techniques have revealed a surprising diversity of planetary systems. Among the most intriguing discoveries are Earth-sized planets located within the habitable zones of their stars. These worlds, often referred to as potentially habitable exoplanets, raise the possibility that conditions suitable for life may exist elsewhere in the galaxy. However, being in the habitable zone does not guarantee habitability. Many other factors, such as atmospheric composition, magnetic fields, and geological activity, play important roles in determining whether a planet can support life. On Earth, life is deeply connected to a complex system of interactions involving the atmosphere, oceans, and geology. The presence of an atmosphere helps regulate temperature, protect against harmful radiation, and maintain stable conditions for biological processes. The magnetic field generated by Earth's interior shields the surface from charged particles emitted by the Sunday plate tectonics, recycles materials, and helps regulate carbon dioxide levels over long timescales. These interconnected systems contribute to the long-term stability of Earth's environment. When considering other planets, scientists look for signs of similar processes. For example, the presence of water vapor in an atmosphere, the detection of certain gases such as oxygen or methane, or unusual patterns in a planet's light spectrum may suggest biological activity. These are known as biosignatures. However, interpreting such signals is extremely challenging, as non-biological processes can sometimes produce similar results. The study of planetary atmospheres has advanced significantly with the development of powerful space telescopes. By analyzing the light that passes through or is emitted by an exoplanet's atmosphere, scientists can identify its chemical composition. These observations provide clues about surface conditions and potential habitability. In some cases, clouds, weather patterns, and temperature variations can also be inferred. Within our own solar system, several locations are considered promising candidates for the existence of life, either in the past or present. One of the most studied is Mars, a planet that once had liquid water on its surface. Evidence suggests that ancient rivers, lakes, and possibly oceans once existed there. Today, Mars is cold and dry, but subsurface water or past microbial life remains a possibility. Another intriguing world is Jupiter's moon, Europa. Beneath its icy crust, there is strong evidence for a global ocean of liquid water. This ocean may be kept warm by tidal forces generated by the gravitational interaction with Jupiter. Similar conditions exist on Saturn's moon Enceladus, which has been observed ejecting plumes of water vapor and ice particles into space. These environments are considered some of the most promising places to search for microbial life within our solar system. The search for life is not limited to planets and moons. It also extends to the study of extreme environments on Earth. Organisms known as extremophiles thrive in conditions once thought to be uninhabitable, such as deep ocean hydrothermal vents, acidic lakes, and frozen polar regions. These discoveries have expanded the definition of habitable environments and suggest that life may be more adaptable than previously thought. The origin of life on Earth remains one of the greatest scientific mysteries. The transition from non-living chemistry to self-replicating biological systems is not fully understood. However, experiments in prebiotic chemistry show that under certain conditions, organic molecules can form spontaneously. These molecules can combine to create more complex structures, potentially leading to the emergence of early life forms. If life can arise relatively easily under the right conditions, then it is possible that it may exist elsewhere in the universe. Given the vast number of stars and planets, even a small probability of life developing could result in a large number of inhabited worlds. This idea is often summarized in discussions of the Drake equation, which estimates the number of civilizations that might exist in the galaxy based on a series of probabilistic factors. Despite the vast potential for life elsewhere, no definitive evidence has yet been found. This absence of detection is part of what is known as the Fermi paradox, which asks why, if the universe is so large and potentially habitable, we have not yet observed signs of extraterrestrial civilizations. There are many possible explanations, ranging from the rarity of intelligent life to the limitations of our current technology and observation methods. Some theories suggest that intelligent life may be rare or short-lived, emerging only under very specific conditions. Others propose that advanced civilizations may exist but choose not to communicate or are using technologies beyond our current understanding. It is also possible that signals from distant civilizations have not yet reached us due to the vast distances involved and the finite speed of light. The exploration of exoplanets and the search for life are still in their early stages. Future missions and telescopes will continue to improve our ability to detect and analyze distant worlds. Instruments capable of directly imaging Earth-like planets, analyzing their atmospheres in detail, and searching for biosignatures will play a key role in this effort. As we expand our search, we also refine our understanding of what life might look like. Life on Earth is based on carbon chemistry and liquid water, but it is possible that alternative forms of life could exist under different conditions. These hypothetical forms of life might use different solvents, different chemical bases, or even entirely unfamiliar processes. Exploring these possibilities helps broaden the scope of astrobiology. The study of life beyond Earth is not only about finding other living beings, it is also about understanding our own place in the universe. By comparing Earth to other worlds, we gain insight into the conditions that made life possible here. This perspective helps us appreciate the rarity and fragility of our planet's environment. The dark matter and dark energy that shape the large-scale structure of the universe also indirectly influence the distribution of galaxies and stars, which in turn affects where planets can form. The same cosmic processes that govern the evolution of galaxies ultimately set the stage for the emergence of habitable environments. From the formation of stars in distant galaxies to the development of planetary systems in quiet regions of space, the universe provides countless opportunities for complexity to arise. Each new discovery of an exoplanet adds another piece to this vast cosmic puzzle, revealing that planetary systems are not rare but common throughout the galaxy. Yet within this abundance, Earth remains the only known world where life has been confirmed. This makes our planet both ordinary in its cosmic context and extraordinary in its biological richness. It is a reminder that while the ingredients for life may be widespread, the emergence of life itself may depend on a delicate and still poorly understood set of conditions. As we continue to explore the universe, the search for life beyond Earth will remain one of the most compelling scientific endeavors. It connects astronomy, biology, chemistry, and physics in a shared quest to understand whether we are alone in the cosmos. Each new discovery brings us closer to answering this question, while also revealing new mysteries. In the next stage of this journey, we will move to the farthest observable reaches of the universe, exploring the limits of what we can see and understand. Beyond these limits lies a boundary shaped not by walls or barriers, but by time, light, and the expansion of space itself. When we observe the universe, we are not seeing it as it is right now, but as it was in the past. This is because light travels at a finite speed, and even though it is incredibly fast, the distances across the cosmos are so vast that it takes billions of years for light from distant objects to reach us. Every observation we make is therefore a glimpse into history, a view of the universe frozen in time. The deeper we look into space, the further back in time we are able to see until we reach the very edge of what is observable. This boundary is known as the observable universe. The observable universe is defined by the distance that light has been able to travel since the beginning of the universe. Because the universe is about 13.8 billion years old, one might assume that we can only see objects up to 13.8 billion light-years away. However, due to the expansion of space described by Hubble's law and the dynamics of the expanding cosmos, the actual observable radius is much larger, extending to about 46 billion light-years in every direction. This means that the observable universe is a vast sphere centered on the observer, containing all the light that has had time to reach us since the beginning of time. At the earliest edge of this observable region lies the faint glow of the cosmic microwave background. This radiation represents the universe as it was only about 380,000 years after the Big Bang, when atoms first formed and light was able to travel freely. Beyond this layer, we cannot see directly because the universe was opaque before that time. This makes the cosmic microwave background a kind of visual horizon, a boundary beyond which electromagnetic observation cannot reach. As we move inward from this boundary, we pass through different epochs of cosmic history. We see the formation of the first stars, the birth of galaxies, and the growth of large-scale structures shaped by dark matter. Each layer of distance corresponds to a different period in time. In this way, the universe is like a layered archive, where each shell of space reveals a different chapter of cosmic evolution. The most distant galaxies we can observe appear as they were when the universe was only a few 100 million years old. These early galaxies are often small, irregular, and rich in star formation. They are very different from the mature spiral and elliptical galaxies seen in the nearby universe. Observing these ancient galaxies allows scientists to study how structure formed and evolved over billions of years. However, there is a fundamental limit to what we can observe. This limit is not just technological but physical. Even if we built infinitely powerful telescopes, there are regions of the universe from which light has not had enough time to reach us. These regions lie beyond the cosmic horizon. They exist, but they are forever hidden from our view because the expansion of space is carrying them away faster than their light can travel toward us. This leads to the concept of the particle horizon, which defines the boundary of the observable universe. It is the maximum distance from which particles or light could have reached us since the beginning of cosmic time. Beyond this horizon, events remain causally disconnected from us. No information from these regions can ever influence our observations, at least under current physical understanding. There is also another type of horizon, known as the event horizon of the universe, related to the accelerated expansion driven by dark energy. Because the expansion of space is accelerating, there are galaxies that are currently visible but will eventually recede beyond the point where their light can ever reach us in the future. Over time, these galaxies will fade from view, not because they disappear, but because space is expanding too quickly for their light to bridge the growing distance. This means that the observable universe is not static. It is slowly shrinking in terms of what we can access from the future perspective of any observer. As time progresses, fewer distant galaxies will remain visible, and the cosmic horizon will become increasingly dominated by nearby structures. In the far future, only galaxies gravitationally bound to us will remain observable. Within the observable universe, matter is distributed in a vast and intricate structure known as the cosmic web. This web consists of filaments, clusters, and voids, all shaped by the interplay between gravity and expansion. Galaxies are not randomly scattered, but are organized along these filaments, forming a large-scale network that spans the entire observable cosmos. This structure reflects the initial conditions of the universe, where tiny fluctuations in density were amplified over time. The farther we look into space, the more we are looking back in time. This allows astronomers to reconstruct the history of the universe by observing different distances. Nearby galaxies represent the present state of cosmic evolution, while distant galaxies reveal earlier stages. By combining these observations, scientists can build a timeline of how the universe has changed over billions of years. One of the most powerful tools for studying the early universe is the observation of the cosmic microwave background. Small variations in its temperature reveal information about the density fluctuations that eventually led to the formation of galaxies. These patterns allow scientists to test models of cosmology and refine our understanding of the universe's composition and evolution. The observable universe also contains regions of extreme interest, such as quasars, which are powered by supermassive black holes, accreting large amounts of matter. These objects are among the brightest in the universe and can be seen at vast distances. Their light provides valuable information about the early universe and the growth of structure over time. Despite the immense size of the observable universe, it may represent only a small portion of the total universe. There is no known reason to assume that the universe ends at the observable boundary. In fact, most cosmological models suggest that the universe extends far beyond what we can see, possibly infinitely. The observable universe is simply the portion that is accessible to us based on the finite speed of light and the age of the cosmos. This distinction between the observable universe and the total universe is crucial. The observable universe is defined by our position in space and time, while the total universe may be far larger or even infinite. This means that what we observe is only a limited sample of the whole, shaped by the constraints of physics and the expansion of space. The concept of horizons in cosmology also has deep implications for our understanding of reality. It suggests that there are regions of the universe that are fundamentally inaccessible, not because of technological limitations, but because of the structure of space-time itself. These limits define the boundaries of knowledge and observation. As we continue to explore the observable universe, we refine our measurements of its size, age, and composition. We use telescopes that observe different wavelengths of light, from radio waves to gamma rays, to capture a complete picture of cosmic history. Space-based observatories allow us to avoid atmospheric interference and observe distant objects with greater clarity. The study of the observable universe also reveals the importance of perspective. Every observer in the universe has their own observable horizon, centered on their location. This means that the observable universe is not a single fixed region, but a relative concept that depends on where the observer is located. However, on large scales, all observers see similar structures due to the uniformity of the universe at its largest scales. As we reach the limits of observation, we encounter fundamental questions about the nature of reality. What lies beyond the observable universe? Is it similar to what we see, or does it contain entirely different structures? These questions remain unanswered as they are beyond the reach of current observation. The interplay between light, time, and expansion defines everything we can know about the cosmos. Light carries information, time determines what we can see, and expansion shapes the boundaries of observation. Together, these factors create the observable universe, a window into the past that reveals the history of everything we see today. Even though the observable universe is vast beyond comprehension, it is still finite. It contains billions of galaxies, each with billions of stars and countless planetary systems. Yet, it is only a small fraction of the total cosmos. Beyond its edge lies the unknown, regions that may never be observed or understood directly. This realization changes our perspective on existence. It shows that our knowledge of the universe is limited not only by technology, but by the fundamental structure of reality. It reminds us that what we see is only part of a much larger whole, much of which may remain forever hidden. As we continue this journey, we move toward the final stage of the cosmic story, where we explore the ultimate fate of the universe. Having seen its beginning, its structure, and its limits, we now turn to its possible endings, where expansion, energy, and time itself may determine the final outcome of everything that exists. The universe, vast and ancient, is not only defined by its origins and structure, but also by its destiny. Every galaxy, every star, every atom is part of a cosmic timeline that stretches from the birth of space and time into an uncertain future. Just as the universe had a beginning, it also has an evolution that continues forward, shaped by expansion, energy, and the fundamental laws of physics. The question of what happens next is not only scientific, but deeply philosophical, because it touches the fate of everything that exists, including time itself. The expansion of the universe, described by Hubble's law, continues to stretch space between galaxies. Over time, this expansion does not simply move objects farther apart, it reshapes the structure of the cosmos. Galaxies that are not gravitationally bound will drift away from each other, becoming increasingly isolated. Clusters of galaxies remain held together by gravity, but everything beyond them slowly disappears from view as space expands. The driving force behind this acceleration is believed to be dark energy, a mysterious component that dominates the large-scale behavior of the universe. Unlike matter, which clumps together under gravity, dark energy appears to be uniform, filling space itself and causing expansion to accelerate. As the universe grows, more space is created, and with it, more dark energy, reinforcing the expansion in a continuous cycle. One possible future of the universe is often described as the heat death scenario. In this outcome, the universe continues to expand forever. Galaxies move farther apart, stars gradually burn out, and new star formation eventually ceases as gas becomes too diffuse. Over immense timescales, even the longest-lived stars will exhaust their fuel, leaving behind white dwarfs, neutron stars, and black holes. The universe becomes darker, colder, and more empty as energy spreads out and becomes less useful for doing work. In this distant future, the night sky would look dramatically different. From any given galaxy, only a few nearby galaxies would remain visible. The rest of the universe would have receded beyond the cosmic horizon, carried away by expansion faster than light can travel toward the observer. The universe would no longer appear filled with countless galaxies, but instead would seem nearly empty, with isolated island galaxies surrounded by vast darkness. Even within galaxies, change would continue. Stars like the Sun, part of the Milky Way, have finite lifespans. Over time, star formation will slow and eventually stop as the gas needed to form new stars is consumed or dispersed. The galaxy will slowly fade as its stars age and die, leaving behind remnants such as white dwarfs, neutron stars, and black holes. Black holes themselves, described by general relativity, are among the longest-lived objects in the universe. They slowly grow by absorbing matter and merging with other black holes. In the far future, they may become the dominant structures in the universe. However, even black holes are not truly eternal. According to quantum theory, they may slowly lose mass through a process known as Hawking radiation, eventually evaporating over timescales far longer than the current age of the universe. If this process continues without interruption, the universe will eventually reach a state where almost all matter has decayed or been absorbed. Elementary particles may also decay, depending on their stability, leaving behind a thin soup of low-energy radiation and extremely sparse particles. The universe would approach a state of maximum entropy, where energy is evenly distributed and no further meaningful work can be extracted from it. Another possible scenario for the future of the universe is known as the Big Rip. In this model, the effects of dark energy become increasingly strong over time. If the expansion accelerates without bound, it could eventually overcome all forms of binding force, including gravity, electromagnetism, and even nuclear forces. Galaxies would be torn apart, then solar systems, then planets, and finally atoms themselves. Space would expand so rapidly that all structures are progressively destroyed. A different possibility is the Big Crunch, a scenario in which the expansion of the universe eventually reverses. If gravity were to dominate over expansion, the universe could begin to contract. Galaxies would move closer together, eventually merging into a dense state. Over time, the entire universe would collapse into a hot, dense condition similar to its original state. However, current observations suggest that expansion is accelerating, making this scenario less likely under present models. There is also a more speculative possibility known as the Big Bounce. In this idea, the universe undergoes cycles of expansion and contraction. A collapsing universe could reach a minimum size and then expand again, possibly giving rise to a new cosmic cycle. This model suggests that the universe may not have a single beginning or end, but instead a series of repeated phases. While intriguing, this idea remains theoretical and is not yet supported by direct evidence. The fate of the universe is deeply connected to its fundamental composition. Ordinary matter, which makes up stars, planets, and living beings, represents only a small fraction of the total content. Most of the universe is composed of dark matter and dark energy. Dark matter shapes the structure of galaxies and clusters, while dark energy governs the expansion of space itself. The balance between these components determines how the universe evolves over time. As the universe continues to expand, the observable horizon changes. Distant galaxies move beyond the reach of observation, not because they disappear, but because their light can no longer reach us. Over extremely long timescales, the universe becomes increasingly isolated. Future observers in distant epochs may only see their local galaxy group with no visible evidence of the larger cosmic structure that we observe today. This raises an interesting implication. The universe may become observationally indistinguishable from a static or empty space in the far future. Without distant galaxies or background radiation, future civilizations might struggle to reconstruct the true history of the cosmos. The evidence for the Big Bang and cosmic expansion could become inaccessible, hidden beyond the cosmic horizon. Despite these distant possibilities, the present universe is still rich with structure and activity. Stars continue to form in molecular clouds, galaxies continue to interact, and black holes continue to grow. The universe is still in a dynamic phase of its evolution, far from its final state. Life exists in at least one known location, and possibly others within this vast and changing environment. The existence of observers within the universe adds another layer of significance to its evolution. Conscious beings are able to study the cosmos, uncover its laws, and reflect on its past and future. This ability to understand the universe from within it is one of the most remarkable aspects of cosmic evolution. It connects the smallest scales of biology with the largest scales of cosmology. The laws of physics that govern the universe appear to be consistent across space and time. This uniformity allows scientists to reconstruct the history of the cosmos and predict its future behavior. From the motion of galaxies to the behavior of subatomic particles, the same fundamental principles apply. This consistency is what makes scientific understanding of the universe possible. As we consider the long-term future, it becomes clear that time plays a central role in shaping cosmic destiny. The universe is not only expanding in space, but also evolving in time. Every moment adds to its history, and every structure within it is part of a larger temporal narrative. From the formation of the first stars to the potential fading of the last black holes, the universe is a story unfolding across billions of years. The concept of cosmic time also raises questions about beginnings and endings. If the universe had a beginning in the Big Bang, then it may also have an end, or perhaps a transformation into a different state. Understanding this timeline is one of the central goals of cosmology, as it seeks to describe not only where the universe came from, but also where it is going. Even in the far future, when stars have faded and galaxies have drifted apart, the universe will still exist in some form. Whether as a cold, empty expanse, a new cycle of expansion, or a radically different state governed by unknown physics, the cosmos will continue its evolution. The details of that future remain uncertain, but the process of change is fundamental and unavoidable. In reflecting on the journey from the birth of the universe to its possible endings, we see a continuous thread of transformation. From simple beginnings, complexity emerged. From energy and matter, structures formed. From these structures, galaxies, stars, planets, and eventually life arose. And from life, the ability to understand the universe itself emerged. The story of the universe is not just a scientific account of physical processes, it is also a narrative of change, connection, and discovery. It shows how everything is linked across space and time, from the smallest particles to the largest cosmic structures. It reveals a universe that is not fixed, but evolving, shaped by both known and still mysterious forces. As this final chapter concludes, it brings together everything that has been explored: the origin of space and time, the formation of matter and structure, the emergence of galaxies and life, and the ultimate fate of all things. The universe is a system in motion, and its story is still being written.